And it is a privilege to give this talk in honor of Professor Srinivasan's 80th birthday. Though by looking at him, I am worried whether the organizers had made some mistake. He does not look any older than 60, and I'm sure that he has many more years of productive life. So I have known him for many years and received lots of encouragements from him. And he's one of those rare scientists who always kept track of what younger scientists in this field were doing and encouraged them in various ways. And also giving the second pedagogical lecture in this workshop after Professor Rodam Narasimha. That is a great honor, but also it's a formidable challenge, which already makes me quite nervous. Anyway, I shall try my best, though I cannot step into his shoes. I shall try my best. Okay, all of you know that turbulence is all pervasive around us. So let me begin by mentioning an example in which you, at the first sight, you may think that it has nothing to do with turbulence. So think of a compass needle, a suspended compass needle. It turns in the north-south direction. So does that have anything to do with turbulence? So if this question is asked, I think most of you probably would say that, no, it seems that it does not have anything to do with turbulence. But it turns out that it's the turbulence in the Earth's molten core which produces the magnetic field of the Earth, and that is what is making the compass needle turn in the north-south direction. And in fact, it was around the year 1600 when William Gilbert, who was a physician in Elizabethan England, he suggested for the first time that the whole Earth must be a gigantic magnet to explain why a suspended compass needle turns in the north-south direction. And initially it was thought that this Earth is Earth's magnetic field is ferromagnetic origin. The Earth must be a gigantic lodestone. But by the middle of, end of 19th century, physicists knew that any ferromagnetic substance loses its ferromagnetism when it is heated beyond a temperature called Curie temperature, and from volcanic eruptions and other things. It was clear that the Earth's interior was much hotter than the Curie temperature of any known ferromagnetic substance. So certainly the Earth's magnetism could not be of ferromagnetic origin, so one has to look for alternative explanations. And also astronomers bothered whether the Earth is a kind of a unique object of astronomical size, a planet which has a magnetic field, or are there magnetic fields in other astronomical systems as well? So until the beginning of 20th century, astronomers knew no method by which they could look for magnetic fields in the other astronomical system. Then around the turn of the century, Zeeman effect was discovered, which all of you might have learned about in your college physics courses. So if you have a source of spectral lines, and if you keep it in a strong magnetic field, then you find that the spectral lines often get split, where you would have one single spectral line in the absence of a magnetic field, you find multiple spectral lines. And just a few years within the discovery of Zeeman effect, in 1908, Hale discovered that the evidence of Zeeman splitting in a spectrum of large sunspot, from which it became clear that a sunspot has a strong magnetic field of about 0.3 Tesla, so which is only a little bit weaker than the magnetic fields produced by strongest electromagnets, but very strong by our standard. It's about 5,000 times stronger than the Earth's magnetic field. So if you have a magnetic field of 0.3 Tesla, you will not be able to hold an ferromagnetic object like a nut or bolt made of iron in your hand in that magnetic field. it will be wrenched out of your hand and get slammed in the nearby pole piece. And during the last century or so, astronomers have realized that magnetic fields are ubiquitous in the astronomical universe. Most planets, stars, and galaxies have magnetic fields. So I don't have time to go into the details of the techniques by which these magnetic fields have been figured out. And then also one big theoretical question is, how do all these astronomical magnetic fields arise? So in this year 1955, Parker formulated the theory of turbulent dynamo, which is still the starting point if we want to understand how these astronomical magnetic fields arise. So certainly dynamo theory has a very big challenge before it. It has to explain magnetic fields of very different kinds. For example, consider the magnetic fields of the sun and the earth. The sun's magnetic field is somewhat periodic in nature. I think even about 5 or 6 decades before Hale's discovery, it was, discovered by an amateur astronomer, Schwabe, that the number of sunspots seen on the sun go up and down in a cyclic fashion. So here is a plot of how sunspot number has varied with time from the year 1600 to 2000. And you can see the early entries are based on records left by Galileo and his contemporaries, who were the first people to study sunspots systematically. And then there was, for several years, sunspots were not seen. And then you see that that sunspot number has gone up and down periodically with a period of 11 years, although there are lots of irregularities. So after this discovery of magnetic field in the sunspots, it became clear that the sunspot cycle is essentially a cycle of the sun's magnetic field. On the other hand, Earth's magnetic field is approximately a static field, although from geological records, we now know that in the past, Earth's magnetic field has sometimes flipped direction. So last reversal took place about 0.78 million years ago. But apart from this reversal, which appeared to be random, between the reversals, Earth's magnetic field is approximately static. So the dynamo theory has to both explain this periodic magnetic field of the sun and also approximately static magnetic field of the Earth and complicated behavior of many other kinds of astronomical magnetic fields. So in this talk, I shall try to give an introduction to dynamo theory and consider its applications to the sun. So why the sun? So first of all, it's my own research field. And secondly, so for the sun's magnetic field, we have a really huge amount of very rich and interesting data. Of course, for the Earth's magnetic field also, we have a huge amount of data. But that being approximately static, maybe not that interesting. So a challenge for any dynamo model is that whether this dynamo model can explain this very rich, interesting observational data of sun's magnetic field that we have. So let me first give a rough introduction to the kinds of data which we have for sun's magnetic field, and then well, I think that was a big debate, but now I think many astronomers have looked at the observatories of old records, and it's more or less established that it was a real thing, that for about 80 or 90 years, sunspots did not appear. And that is a big challenge of dynamo theory to explain that. But of course, in this elementary talk, I shall not be able to get into that, but that's a very challenging theoretical question. And as I go ahead, if there are any questions, please feel free to stop me. So let me tell you a few things about the sun's magnetic field before we come to theory. So a few years after Hale's original discovery of magnetic fields in sunspots, Hale and his collaborators made another very important discovery. Often we see two large sunspots side by side. So Hale et al. Found that in such cases, usually the two sunspots have opposite polarity. If one has positive polarity, other has negative polarity. And the most plausible explanation for that is that maybe there is a strand of magnetic field underneath the sun's surface, which is poking its nose through the sun's surface in this way. So these two intersections of the strand of this magnetic field with the solar surface. So if these are the two sunspots, then in one sunspot we have magnetic field lines coming out, making it a positive polarity sunspot, and the other sunspot will have field lines going down, making it a negative polarity sunspot. So in a few minutes, I shall come to the theoretical consideration how such magnetic configurations arise. And then now let me show you something very fascinating, a magnetogram map of the solar disk. So a magnetogram is something which measures the magnetic field at every point of the solar disk. And if the magnetic field is positive, then white color is put. If it is negative, then black color is put. And gray means that the magnetic field was very weak. So in some places, you will see white and black side by side. So this means that here are these two sunspots here. And since one sunspot has positive polarity, it's appearing as white, and the other sunspot has negative polarity, appearing at black here. And you see that in northern hemisphere, here you have a white appearing in the right and black on the left. And in the southern hemisphere, you have opposite polarity, black on the right and white on the left. And it remains like this for about 11 years. So if you took a magnetogram map 11 years earlier or 11 years later, then you will find that in the northern hemisphere, black will come to the right and white to the left, and the southern hemisphere also it will be reversed. So if you just look at the number of sunspots, you may think that the cycle period is 11 years. But if you also consider the direction of the magnetic field, then the actual cycle is approximately 22 years. Now, looking at this distribution of magnetic field on the solar surface, you get a feeling that in the northern hemisphere of the sun, that there must be magnetic field underneath the surface going like this. So if in some place it is coming out to the surface, this on this side you will have field lines coming out, making it a positive polarity sunspot, and on this other side you have field lines going down, making it a negative polarity sunspot. And in the southern hemisphere, the magnetic field underneath the surface should be going in this direction to produce opposite polarities. So in other words, you expect that underneath the sun's surface, the magnetic field should look like this, and coming through the surface in various regions is producing this kind of magnetic distribution. And in the jargon of dynamo theory, this kind of a magnetic field is called a toroidal field. And whereas we believe that the Earth's magnetic field is probably somewhat like this. This is called a poloidal magnetic field. And in this famous paper, 1955, Parker suggested that the sun's magnetic cycle is produced by a kind of oscillation between the toroidal and poloidal magnetic fields. So somewhat reminiscent of the oscillation between potential and kinetic energy that you see in the simple harmonic oscillator. So this was a really bold suggestion at that time, because at that time people were not even sure whether the sun has a poloidal field. And in fact, in this very same year, 1955, Babcock and Babcock, a father and son pair of astronomers, for the first time discovered that there is a magnetic field in the sun's polar region also. So that turns out to be much weaker than the sunspot magnetic field and more difficult to detect. So it's something like 10 to the power minus 3 Tesla. So this question is, do we have this kind of oscillation between toroidal and poloidal magnetic field, which Parker suggested? So that could be established only many decades later. So here I show you the data of relevant data. So the solid and dashed lines indicate how the north polar magnetic field and south polar magnetic field, how they have varied with time during the last 30, 40 years. And below that, you see a plot of, I think, sunspot number. So you can see, remember that the sunspots, as I pointed out, that the sunspots form out of this toroidal field. So the sunspot number is a sort of a measure of a strength of the toroidal field. So you see that the sunspot number of the toroidal field is strongest at a time when the polar field or the poloidal field is close to zero, and the polar field or the poloidal field is strongest at a time when the sunspot number or toroidal field is very low. So we really see the kind of oscillation between toroidal and poloidal field, which Parker envisaged several decades before this could be established from observational data. So it's mind-boggling to think what kind of theoretical insight a person would have to come up with such an idea several decades before it was established. So that means that if we want to develop a theory of the sun's magnetic field, then we have to explain how from a toroidal field we can go to a poloidal field, and how from a poloidal field we can go to a toroidal field. Now, before getting into theory, let me just tell you what the sun's interior is supposed to be like according to theoretical consideration. So sun's center is supposed to be at a temperature of about 15 million degrees, where energy is generated by nuclear fusion, hydrogen getting converted into helium, and then up to 0.7 solar radius, there is a region where this energy is transmitted outward through a process called radiative transfer, which means that photons essentially random walk through stellar matter. And from theoretical consideration, it's found that from 0.7 solar radius to the surface, this region is unstable to convection, and heat is transported in this region through convective heat transport. So sunspots are essentially magnetic structures sitting in the turbulent convection zone, and it's as we shall see, it's the turbulence of the convection zone which drives this dynamo process. So with this introduction to this observational data of the solar magnetic fields, let me now come to the theory. So the material inside the sun is in the plasma state, and a plasma is essentially a fluid which is a good conductor of electricity. And if it's a good conductor of electricity, there can be electric currents, and they will produce magnetic fields. So when you study the dynamics of electrically conducting fluid, you essentially have to combine the equations of fluid mechanics with the equations of electromagnetism. And that combination is known by the tongue-twisting name Magnetohydrodynamics, abbreviated as MHD. So I'm assuming that all of you are familiar with fluid dynamical equation, but I don't know whether all of you have some exposure to MHD. So how many of you do not have any previous exposure to MHD? Please raise your hands. Okay, so I see that majority of you. So maybe I should to give a little bit of introduction to MHD, because there will be several talks in this workshop later. We'll be dealing with MHD, and though I have the equations written down there, so as a teacher I always like to explain things on the blackboard. So maybe quickly I shall write some things on the blackboard, so you know that the basic equation of fluid mechanics is this Navier-Stokes equation. And in this Navier-Stokes equation, so what is if we have electromagnetic field, so what should be the extra term that we have to put? So you are all familiar with that. And what is the extra term we have to put? So if you remember your electromagnetism textbooks in high school or college, then you would remember that the electromagnetic force per unit volume is given by this expression. So charge density, electric charge density multiplied by E, and then current density cross B. And in the case of the plasma, we can usually forget about this term. So why this term? For the same reason in which in electrostatics problems, which you must have solved, we can, inside a conductor, we assume that the charge density and electric field to be 0. Because if there is an electric field inside a conductor, that will make the charges move until the electric field is neutralized, and then the charges reside only on the surface of the conductor. So exactly for the same reason, inside a conducting fluid, the charge density or electric field will be negligible. So we only have to add this term to this equation. And also we know that the current density and magnetic field are related to each other by one of Maxwell's equations. And this is the famous displacement current term, which was introduced by Maxwell and which is crucial for Maxwell's derivation of electromagnetic waves. But here we are considering motions of plasmas which are much slower than the speed of light. So in such situation, it turns out that this term is unimportant, and then it is called a MHD approximation. And if this term is unimportant, then you see that the J will be curl B divided by mu 0. So this is going to be curl B by mu 0 and cross B. And by a simple identity of vector analysis, you can show that this term is going to be equal to this. So these are the terms which are put in this equation. So you can see that this term can be combined with the pressure gradient term. So the significance of this term is that the magnetic field also exerts a pressure. So there is a magnetic pressure coming, and the significance of this term is that it is of the nature of a tension force. So if you consider a uniform magnetic field, it is very easy to show that this term will be 0 for the uniform magnetic field, because B dot grad means we are taking a derivative along magnetic field line. So along this direction, and its magnetic fields lines are straight. So as you move along this direction, there is no variation. So for straight magnetic field lines, this term will be 0. So only when magnetic field lines are bent, this term will arise, and this term will try to reduce the bend in the magnetic field. So this term is of the nature of tensions. So remember that the importance of magnetic field is that it introduces a magnetic pressure in the Navier-Stokes equation and also magnetic tension. And so certainly this magnetic field would affect the dynamics, and also we expect the dynamics also to affect the magnetic field. So we need a sort of a time evolution equation of the magnetic field. So how do we get the time evolution of the magnetic field? And one of Maxwell's equations is this. This curl E, and I already pointed out that the E inside the moving fluid, at least in its race frame, will be very small, and we also can that small field also can be written in terms of magnetic fields and velocity field. How? So you all must be familiar with Ohm's law, one of the very important laws of electricity magnetism. So in the case of a continuum, the Ohm's law can be written in this fashion. But when we are also continuous substance like a fluid, when there is a motion, then you know that the force on a charged particle is rather than E, it is E plus V cross B. So this is the case of this is the Ohm's law for this moving fluid, and from this you can easily see that E is going to be this J dot sigma minus V cross B, and then for this J you can again put this curl B mu 0. So if you substitute this expression of E in this equation, and then you get what is the central equation of MHD, known as known as induction equation. So from this you get this term, two minus signs cancel each other, and here you put the curl of that. For simplification, if you assume that mu is spatially constant, then this will give you. So this is the equation which tells you how magnetic field evolves in time as the central equation of imaged induction equation. And since you people are not familiar with this equation, let me tell you a little bit about the significance of this equation. So first of all, you can see that what will be the order of magnitude of this term. So for this term, I think if we, velocity field is velocities of the order of capital V and magnetic field of the order of capital B. And since this involves a sort of taking a curl, so that will put taking a derivative with respect to space. So if L is the typical length scale, then this term is of this order. And then this term, you can see that it is of this order B. So since it's a double derivative, L squared will come. So this term is of this order. And this ratio of these two terms is called magnetic Reynolds number, often also called Lundquist number. So you can see that this ratio of these two terms, it has this kind of an expression, and it goes as the length scale of the system. So which means that for astronomical systems, this number is very large, and for laboratory systems, not so large. And in fact, if you put typical numbers for various quantities, then you find that for laboratory system, this number is much, much less than 1, which means that this is the dominant term. So magnetic field behaves approximately this way. And for astrophysical system, it turns out that because of the large L, this number is usually much larger than 1. And in such situation, this is the dominant term. So magnetic fields are governed by two very different equations in the laboratory situation and the astrophysical situation. So this is the diffusion equation which you recognize, where the inverse of resistivity or inverse of conductivity, sigma is the conductivity, resistivity appears as the diffusion coefficient. So which means that resistivity makes the magnetic field decay. And its interpretation is obvious that when you have currents through a plasma, these currents will produce magnetic field. But if you don't have anything to sustain the current will decay due to resistance, and as a result, magnetic field also will decay. So this is a simple interpretation. So now let us look at the physical significance of this term. And many of you may recognize that that in fluid mechanics you have a equation for vorticity, which looks very similar to this equation. And out of this equation, you have this famous Kelvin-Helmholtz theorem of vorticity. So out of a similar equation of magnetic field, you also have a very similar theorem, which was first enunciated by Alfven. So instead of this approximation, if we have exactly this equality, then out of this equation, one can prove Alfven's theorem of what is called Alfven's theorem of flux freezing. That is the MHD analog of Kelvin-Helmholtz theorem. So its theorem is not too difficult to prove, but of course in this short presentation I shall not get into the proof. So I shall again just make the statement, and those of you who are familiar with Kelvin-Helmholtz theorem will realize that it's very similar to Kelvin-Helmholtz theorem. So suppose inside a magnetofluid, you consider a sort of a surface, so A, B, C, and there is suppose some magnetic flux going through this at some time T1. So you have this magnetic flux through this surface B dot ds at time T1. And if there are motions in the fluid, so after some time, so A will go here, will become A prime, B will become B prime, etc. C will become C prime, and the surface after some time, so T2 will take up this kind of a configuration at time T2, and there will be a magnetic flux through it. So at time T2, you consider the magnetic flux through this surface, and according to Alfven's theorem, if this equality holds here, then these two fluxes, they are going to be equal to each other. So if there was a surface in the magnet fluid here with a magnetic flux, then when that surface moves here, the same magnetic flux will have to be there. So magnetic field moves with the fluid. So here I consider an illustration of that. So suppose you have some highly electrically conducting substance between the pole pieces of some magnet, and suppose you move it, and then what happens? So if low magnetic Reynolds number situation, nothing much happens. This material is taken out and the magnetic field is there. But in high magnetic Reynolds number case, Alfven's theorem has to be satisfied. So if you consider some surface inside, hypothetical surface, whatever is the magnetic flux, so when that hypothetical surface comes here, the same amount of magnetic flux has to pass through it. And that can happen only if the magnetic field takes up this kind of a configuration. So that means that in a high magnetic Reynolds number situation, with the fluid motions, I think magnetic fields can be deformed and twisted and dragged. So its behavior is very different from the behavior of magnetic field we are familiar with from our laboratory experiment. So Alfven coined the phrase cosmical electrodynamics to describe electrodynamics at cosmical scales. And in fact, he wrote a very influential monograph on this subject titled Cosmical Electrodynamics. And he also won the Nobel Prize for his contributions to this field. And now let us again take a look at this induction equation. So suppose through this MHD we are trying to explain why the Earth has a sort of a static magnetic field. So if this is a diffusion term, so if this term where the velocity field can drag magnetic field, so it's somehow that effect can balance the decay term, then if these two terms balance each other, then magnetic field will be static with respect to time. So is it possible to have a solution of this equation that these two terms together equal to 0? So these two things equal to 0, then we would have a static magnetic field. And Cowling is one of the first persons who looked at the problem, and he established a theorem called anti-dynamo theorem, that if he showed that if velocity field and magnetic field are both axisymmetric, then this equation does not admit of a solution. So that produced some consternation. Some people thought that, oh, we have to now look for more complicated solutions, which are, since axisymmetric solutions are ruled out. And some people thought that maybe it's a special case of a more general theorem, that maybe it's not possible to sustain magnetic fields in the fluids with fluid flow motion. And then eventually this problem was solved by Parker, who showed that if there is a turbulence, then the turbulence introduces non-axisymmetry, and that non-axisymmetry is crucial for solving this problem. So now let us, before coming to this crucial thing of dynamo theory, let me now start applying MHD to the sun. So first question is that why do we have in sunspots, we have magnetic fields concentrated in a region rather than magnetic fields filling up all space? So I've already pointed out that the sunspots are sitting in regions of turbulent convection. So all around here you see some kind of a granular structure. So these are nothing but convection cells on the surface of the sun. So to understand why magnetic fields confined in a region, we need to study the interaction of magnetic field with convection. That subject is called magnetoconvection, of which the linear theory was developed by Chandrasekhar, and then nonlinear evolution is studied by people like Weiss and others. So suppose you consider a magnetofluid with a vertical magnetic field which is heated from below. So you know that when the temperature gradient is sufficient, you expect that convection will start. And I already pointed out that the magnetic field has tension associated with it. So because of this tension, it is more difficult to start convection when there is a magnetic field. So critical Rayleigh number for starting convection will, in this case, will be higher than critical Rayleigh number in the absence of magnetic field. And when convection starts, you find that the nature finds it expedient to divide space into two kinds of regions. In certain regions, magnetic field lines are excluded and convection takes place freely. And in the other regions, magnetic field lines are confined together and convection is suppressed. So these regions are, such regions are called magnetic flux tubes. So since convection is suppressed here, the tops of these regions become colder than this region. So sunspots are believed to be such magnetic flux concentration produced by interaction with convection. And since heat transport is suppressed, that's why these regions have lower temperature. And you know that that the brightness goes as fourth power of temperature. So this lower temperature causes the darker appearance of sunspots. And we believe that throughout the sun's convection zone, the magnetic field exists in the form of flux tubes because of interaction with the turbulence in the convection zone. And now we come to this again, this toroidal and poloidal magnetic field. So if we write down the magnetic field in spherical coordinate, then the phi component is the toroidal component, and this r theta component together is the poloidal component. So as we have seen that there is a oscillation between these two components in the sun. So somehow we have to get the toroidal component from a poloidal component and then get back poloidal component from the toroidal component. So let us consider a situation that first, suppose we had just poloidal component and sun also rotates about its axis like the earth. But whereas the earth rotates nearly like a solid body, the sun has what is called differential rotation. There's a variation of angular velocity. So a point near the sun's equator would take about 25 days to go around the rotation axis, but a point near the sun's pole would take close to, I think, 35 days to go around the rotation axis. So because of this differential rotation, the equatorial region is moving faster, and that will try to drag the magnetic field line. So exactly what we saw here. Why is it not? So exactly what we saw here, that is. Yeah, that's right. So exactly what happened here, the way magnetic field lines got dragged, exactly the same thing will happen. Poloidal field line will get dragged, and you see that out of poloidal field line, here we have got toroidal field lines, and this toroidal field is opposite and this toroidal field is opposite in the two hemispheres. So parts of this toroidal field would rise to produce bipolar sunspots. You can easily see that they will have opposite polarities in the two hemispheres, as you saw in the magnetogram map. So the question is, why would parts of this toroidal field would rise to the surface? So again, first question for that is that where is where inside the sun this toroidal field will be produced. And certainly you expect the toroidal field to be produced in a region where there is a strong gradient of angular velocity, strong differential rotation. And there has been a development in the last few years called helioseismology, about which several speakers will probably speak later. So from helioseismology, we now know that there is a strong differential rotation at the bottom of the sun's convection zone. So we believe that the strong toroidal field would be produced there, and due to interaction with surrounding convection, it will exist in the form of a flux tube. So if we consider a flux tube, there will have to be a pressure balance inside and outside. And inside you have gas pressure, and plus as you saw, that magnetic field also has a pressure. So magnetic pressure, but outside you just have gas pressure. So this will be a pressure balance equation inside and outside of the flux tube. And this means that pressure inside has to be less than pressure outside, which very often, though not always, implies that the density inside should be less than density outside. And Archimedes taught us more than 2,000 years ago that inside a fluid, if you have something with density less than the surrounding density, then it will become buoyant and come up. And again, this idea of this magnetic buoyancy was proposed by Parker in the same year, 1955, in which he wrote his fundamental paper on the dynamo. So he also showed that magnetic buoyancy is particularly destabilizing within the convection zone, but can be suppressed to some extent below the bottom of the convection zone. So suppose you have, I pointed out the flux tubes form near the bottom of the convection zone. So suppose in a flux tube, a part comes within the convection zone, then that part will become buoyant and rise, whereas these other parts will remain anchored. So after some time, this part will come to the surface and produce these two bipolar sunspots. And as we saw that this toroidal field has opposite sign in the two hemispheres. So that will, when bipolar sunspots form from it, they will have opposite polar distribution in the two hemispheres, as you saw in the magnetogram map. So then, I think starting from the poloidal field, we can, by combining the ideas of flux freezing, magnetoconvection, and magnetic buoyancy, we can explain various features of sunspots that due to flux freezing, it will be dragged to produce the toroidal field, and then due to magnetoconvection, it will be confined in flux tubes, and due to magnetic buoyancy, it will rise to the surface. But but you have to maintain the poloidal field for that process. And also to produce the magnetic cycle of the sun from the toroidal field, you have to go to the poloidal field. So how does that happen? So the crucial ideas given by Parker and then developed further by Steenbeck, Krause, and Radler. So suppose you have from a poloidal field, this kind of a toroidal field has been produced. And since it's in a convection zone, there we know that hot fluid is going up and cold fluid is coming down. So suppose as a hot fluid is going up, so since it's a situation of high magnetic Reynolds number, it will try to drag the magnetic field like this. And as it is dragging the magnetic field and going up, it's also, since it's a rotating frame of reference, it will also have a sort of a rotating cyclonic motion, just like cyclone in the Earth's atmosphere. So as it is going up, it is also rotating, and that's why it will be, because of this helical motion, and it will twist the toroidal field in this fashion, so that you will get some sort of a loop in the poloidal plane. And if you keep in mind the fact that the toroidal field has opposite sign in the two hemispheres, and in the two hemispheres also, the Coriolis effect will have different signs. So from this combination of that, you can show that these loops in the two hemispheres will have the same sense. So you can consider many such loops, and since there is a diffusion in the system, so these loops will eventually diffuse and give rise to a large-scale poloidal magnetic field. So I believe this is how from a toroidal field, the poloidal magnetic field is produced. So this is often called alpha effect, because in the mathematical theory, it is expressed by a coefficient alpha. And one requirement for this is that the toroidal magnetic field should not be too strong, because the magnetic field has this tension. If the toroidal magnetic field is too strong, then its tension will be so strong that convection will not be able to twist it. So essentially, the one condition is the toroidal field energy density should be less than the kinetic energy density of turbulence. So basically then, in Parker's picture, this toroidal field and poloidal field of the sun sustain each other through a feedback loop. From a poloidal field, due to differential rotation, you get a toroidal field, and from toroidal field, by helical turbulence, you get the poloidal field. So from this classical model, I think many aspects of the solar cycle could be explained quite nicely. But then eventually we realized that the classical model is not a completely correct model because if the toroidal field is too strong, then it is not possible for this alpha effect to operate. So due to some numerical simulations of magnetic buoyancy which we carried out, we realized that the toroidal field would be much stronger than what was originally expected. So this original model of a solar dynamo classical model cannot work because if the toroidal field is so strong and the turbulence cannot twist it. So then we realized that there is a way of modifying the theory called flux, which gives rise to something called flux transport dynamo model. And though this was a development initiated by us and then many other groups took it up. So I would have been very happy to speak about this flux transport dynamo model, but I realized that in this 1-year pedagogical lecture, I won't have time for it. So I shall just won't get into this flux transport dynamo model. I shall just discuss a little bit about this classical model in the next 5 minutes or so. So anyway, I may mention that these two papers from our group, they have by now more than 400 citations according to Google Scholar, making them two of the most highly cited papers in theoretical solar physics in last quarter century. Anyway, so I won't be able to get into the details of that. Let me restrict myself to the classical model. Even though we now know that the classical model was not completely correct, it was historically very important, and pedagogically, if you are learning this subject, pedagogically, it's very important to know a little bit about the classical model. So anyway, in this classical model, this poloidal field is produced by this sort of alpha effect. So since you have this turbulence here producing this alpha effect, producing this poloidal field, so the question is, how do you develop the mathematical theory? So basically, you average over turbulence to develop the mathematical theory. So you split both the magnetic velocity field and magnetic field into an average part and a fluctuating part, and substitute this in the induction equation, which I have again written down. So you see that then you will get this equation. So you see that from V cross B, this term, writing V and B like this, you will have 4 cross terms like this. And now suppose you average this equation term by term. And you remember that the fluctuating parts, V prime and B prime, their average should be 0. So certainly when you average this term involving B prime goes to 0, and then this term remains there. And when you have this kind of a term, that V average plus B prime, and take the whole average. So this is already average. So this means that you have to average of that, and that average is 0. So average of this term and that term will go to 0. So only the question is what will happen to this term. So I'm coming to that. So this term we can write like this. It's called mean EMF. So I'm writing this like that. And then from this term on averaging again, B prime will go away. So this is a formalism of mean fields, which was developed by these East German scientists Steenbeck, Krause, and Radler. So now to proceed further, we have to figure out whether this term is going to be 0 or non-zero. So you can easily figure out that if V bar and B bar, if they do not have any correlation, if they are uncorrelated, then this term will be equal to 0. If they are uncorrelated, then we would have. If they were uncorrelated, then V prime cross B prime, this then would have been like this, and both of these are 0. So they will be non-zero only if there is a correlation. So do we expect a kind of a correlation? It turns out that we expect a correlation because of this flux freezing theorem. So if there is a fluctuating velocity field, so that will try to drag the magnetic field and produce a sort of perturbation in the magnetic field. So these are correlated. So somehow you have to evaluate this term. So that is called a closure problem in a mean field theory. And Steenbeck, Krause, Radler developed a procedure called first order smoothing approximation, fossa. I don't have time to go to the details of that. From this fossa, they showed that this EMF of this mean EMF can be expressed in this form, that in terms of this average magnetic field, and this alpha and beta, these are coefficients which are related to the turbulent velocity field in this way. So beta is like the energy density of turbulence, and alpha is V prime dot curl V prime. So it is like a helicity. So as in a convection, as the fluid is rising, if it is rotating, then you will have also curl V in this direction of rise, and then V dot curl V will be non-zero. So it's the measure of helical motion in the fluid. So if E is given by this expression, then again in this expression, if you for this curly E, if you put this, and then you get this, and so you can see that this beta term goes with the diffusion. This is nothing but the turbulent diffusion, and this alpha coefficient appears in a term like this, and that is the crucial dynamo generation term. So we often, since we have to write velocity field and magnetic field many times, so we often drop the overline to make our notation simple. So we can write this equation in this form, and where this term is this turbulent diffusion lambda d, so which is the dominant term. And this is the celebrated dynamo equation, mean field dynamo equation, and lots of research in the dynamo theory was done on the basis of the mean field dynamo equation. Tau is the correlation time of turbulence. Okay, so again, I don't have time to go into the details of the solution. So I shall just mention that to make a model of either geodynamo or solar dynamo, you have to write down this mean field dynamo equation in spherical coordinate. So I shall just show what it looks like. This dynamo equation is spherical coordinates. You write the magnetic field like this. This is the toroidal component, and the poloidal component can be written from a scalar function like that, and velocity field can be written like this. This V is the r theta component, and the phi component comes from the angular velocity, which can be written like that. Then if we substitute V and B written in this way in this mean field dynamo equation, then you get these equations for the toroidal and poloidal field. So this gives the equation of poloidal field, and this gives the evolution of the toroidal field. So you see that both have diffusion equation, and these are the source star. So for the case of the poloidal field, the source star involves this alpha, which is the measure of this helical motion. So this helical motion operating on the toroidal field produces the poloidal field, which was that equation is a mathematical representation of what you saw here. It is a mathematical representation of that, and you see that the generation term of the toroidal field has two terms. So this term has the gradient of omega. So this has the differential rotation. So the differential rotation produces the toroidal field from the poloidal field, and the toroidal field also can be produced by this alpha effect. So this comes from that. And so there are these two terms, T1 and T2. So in a system like Sun or the stars where the differential rotation is strong, then this is the dominant term. And if T1 is a dominant term, that is called an alpha omega dynamo, because one source term has alpha and one source term has omega. And on the other hand, in the planets like the Earth, there is not much differential rotation, so that term is negligible. So if T2 is the dominant term, then it's called an alpha squared dynamo, because alpha appears in the source terms of both these equations. And though there is not a rigorous theorem, it's found that most of the alpha omega dynamo equations tend to give oscillatory solution, and alpha squared dynamo tend to give static solution. So that's why we believe that the behavior of the solar dynamo and geodynamo are so different. So I have discussed this sort of I think, mean field equation, and one big effort in the last few years has to do direct numerical simulation, since turbulence is also produced by by fluid dynamical equation, Navier-Stokes equation. So from first principles, can you do the simulations and simulate turbulence and dynamo process together? So for the sun's case, it is still a very complicated problem. So there is so far very limited progress doing DNS of the sun's dynamo. But for the geodynamo, in the last 20 years, there have been some impressive simulation. One famous simulation was by Glassmeyer and Roberts, and then their geodynamo simulation, they were able to get reversal, like this geomagnetic reversal. So here is the figure from their paper, how it evolves in time. So these orange and blue are the two signs of a magnetic field. So you saw that in the simulation, in this way, reversal took place. Okay, so I think I shall stop here by drawing your attention to a couple of my books if you want to learn more about this subject. So this is I think a popular science book which gives a non-technical introduction to phenomenology of sunspot cycle and dynamo theory. And this is a graduate level textbook. So if you want to learn the basics of mathematical theory of this dynamo process, then all the theorems which I quoted without giving any proofs, all these things are discussed in this book. So with that, I shall stop, and if the chairman allows, maybe a short time for questions.
I think we'll take a few questions, and as I said again, this is a long workshop. You will have plenty of time to talk to the speaker, but if you have some simple questions, yeah.
So you have mentioned about the differential rotation term.
Yes.
I'm just confused whether it's a Coriolis term.
Oh, well, Coriolis term, that is because what we are doing is called a kinematic approach. So Coriolis term will appear in Navier-Stokes equation in a rotating frame. So what we are doing is called a kinematic approach. So there we are assuming that somehow the velocity field is given and statistical properties of the turbulence is given, and we are solving only for the magnetic field. So only when we are solving for the magnetic field, the Coriolis term does not appear. It appears in the Navier-Stokes equation. But of course, when one does this sort of a full DNS, there one solves Navier-Stokes equation also along with induction equation. There Coriolis force plays a very important role.
Thank you.
As chairman, using chairman's prerogative, I'll just mention something, and you tell me if this is relevant. In classical mechanics, in springs, there is a particular kind of pendulum called Wilberforce pendulum. And this is basically a coil, which if you set it in torsional motion, the torsion actually also produces an elongation of the coil. And the mode of the pendulum goes from pure torsion to pure longitudinal mode with a period. And you can do this coupling between one mode and another mode, but that's it's a static thing. It's not being driven by a pendulum thing. So is this, and you can do this in many different, coupling of oscillator thing. So is it possible to do all of this as a kind of a time averaged kind of static problem, this poloidal and the toroidal coupling thing, or is it entirely can you get the period of going back and forth as a regular answer? Standard answer?
I think to some extent. So I also gave this analogy that I think this Wilberforce pendulum which you mentioned, that's also this stretching and this twisting. So here also you have this stretching and twisting. So this analogy is quite interesting, but this analogy should not be pushed too far, because in the pendulum it is a sort of a conservative system. The energy is conserved and it is moving with the energies getting exchanged. So here it is not a conservative system since there is a diffusion in this system. So energy is continuously dissipated and from the turbulence in the convection zone, energy is being put into the system. So this is in that sense not a conservative system. So in a system there's a continuous decay and turbulence is pumping continuous energy. So there are, I think, interesting analogies with this mechanical problem, but one should also keep in mind that this analogy should not be pushed too far.
Yeah, Srini.
There are these various, I think, coefficients, I think turbulent diffusion and there's alpha coefficient of which we do not have that much knowledge what are the exact value. So by choosing these parameters suitably with assuming reasonable values for them, you can get 11-year period.
Yeah, so one short question about the time scales that is associated with the fluid as well as the magnetic field. So if you're trying to compute, are they going to be two different time scales or?
Yeah, that's right. So typically in a convective turbulence, the time scale is of the order of a few days. And as you saw that magnetic field evolution time scale is of the order of several years. And in fact, in mean field theory, one crucial thing is that you need to have this scale separation. So certainly because of this scale separation, that the fluid motions which are causing this dynamo action and the time scale of dynamo, they are quite different. But in the mean field theory, I think another thing is that you expect fluctuations should be smaller than the average, but that is not the case. So certainly the sunspots are like big fluctuations in the magnetic field. So fluctuations are much larger than the mean. So that question always bothered a mean field theory, that when there are fluctuations are much larger than the mean, should the mean field theory work? So we don't have any rigorous mathematical answer, but in many theories in physics, it often happens that you cannot give a rigorous mathematical justification, but somehow mysteriously a theory seems to capture the truth. So I think something like that is happening.
Time scales between the velocity field and the magnetic field, are they different or?
Yeah, the velocity field, as I said, that convection time scale is of the order of a few days, and the magnetic field changes in the time scale, mean magnetic field in the time scale of a few years.
Sir, how good is the assumption of How good is the assumption of taking a sun, the material inside the sun to be a conductor, like a perfect conductor, like as following the Ohm's law?
Well, it's the material there is in a plasma state, and plasma is always a very good conductor of electricity. Plasma means electrons have come out of atoms, and atoms become positively charged ions. So if you put an electric field, ions move in this direction and electrons in the opposite direction. So certainly it's a plasma material is a very good conductor of electricity.
Yeah.
About your DNS simulation in the direct.
Not my DNS simulation.
I was just going to ask, do you actually get realistic astrophysical parameters in the handle the equations, or do you?
Well, no, I think even in the case of I think Binod Srinivasan, he's not here yet. He will be giving a talk. I think he's supposed to attend. So he has been in IS, he has been doing this. So in the case of the Earth also, these various Rayleigh number or Ekman number or things like that. We are still, I think, orders of magnitude removed. I think in the case of the geodynamo, we are something like 3 or 4 orders removed from the actual values. But in the case of solar dynamo, these are more like 10 or 12 orders of magnitude we remove. So that's why doing DNS of solar dynamo is much more difficult than doing DNS of geodynamo.
But could you capture, I mean, I understand that the scale is different, but to the extent you can do a scale transformation, is it possible to say that you are capturing the essence of the phenomena?
Well, that is also, I think, subject to debate. So certainly the important, I think, dimensionless numbers there, I think those dimensions in the simulations, as I said, that those dimensionless numbers are orders of magnitude different. But in the case of geodynamo, we feel that the difference is not so large, so we are capturing some essential physics. But in solar dynamo, DNS calculations are very far from modeling the solar magnetic fields realistically.
Let's take the last question here.
Resistive scale or
Well, resistive scale means if you consider the resistance coming out of this molecular thing, then that resistive scale is very, very large. But with the turbulent time scale, it has to be, for example, a sunspot also, typically a sunspot lives for something like, I think, 10 days or so. A sunspot also has to decay. So if it were decaying by molecular processes, then a sunspot would live for years. So only when you put turbulent diffusion, then the decay scale comes out to be reasonable for the order of a few days.
Srini, did you have another question?
If I may. The excitement about Glatzmeyer's calculations was the qualitative understanding of the reversal of the magnetic field of the Earth and linking it to convection, which was a very exciting thing.
Well, this brings us to the end of this session, right? So let's thank both speakers for giving us a great start.